Okay, the first thing that we're going to talk about today is instantaneous and average power in multi-frequency circuits. So let's consider a linear black box system with two terminals. That is excited by some form of signal generation, such that there is a time domain voltage V of t across the network's terminals and a time varying current I of t flowing into the network's terminal. And in this case, we are going to say that V of t is of the form Vm1 cosine omega 1 t plus theta V1 plus Vm2 cosine omega 2 t plus theta V2. I'm going to call this part VA of t and this part VB of t. And our current will also be composed of multiple frequency components. So that'll be Im1 cosine omega 1 t plus theta I1 plus Im2 cosine omega 2 t plus theta I2, where we'll call this part IA of t and this part IB of t. The instantaneous power that's absorbed by our network, P of t, will be simply the product of the voltage waveform and the current waveform. So V of t times I of t. And I can break this down and say that this is going to be VA of t times IA of t plus VA of t times IB of t plus VB of t times IA of t plus VB of t times IB of t. So effectively, we're going to FOIL out this multiplication of sinusoids. Now, we're going to use the same trig identity here that we used when we covered instantaneous and average power for a single frequency circuit. As a reminder, that trig identity, I'll tuck it in right here, is cosine of angle 1 times cosine of angle 2 looks like 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. So applying this trig identity, what we're going to get when we multiply VA times IA will be 1/2 VM1 IM1 cosine theta V1 minus theta I1 plus 1/2 VM1 IM1 cosine twice omega 1t plus theta V1 plus theta I1. When we multiply VA by IB, we're going to add to our previous term a factor of 1/2 VM1 IM2 cosine. And so here we're going to subtract our angles, okay? So our angle 1 is omega 1t plus theta V1, and our angle 2 is omega 2t plus theta I2. So this is going to look like omega 1 minus omega 2t plus theta V1 minus theta I2. And then we're also going to have the second part of applying our trig identity. So that's a 1/2 VM1 IM2 cosine. And now I add the angles together. So that's omega 1 plus omega 2t plus theta V1 plus theta I2. Now we're to the point where we are multiplying VB times IA. So let's tuck that in right here. So that's going to be VM2 IM1 cosine omega 2 minus omega 1t plus theta V2 minus theta I1 plus 1/2 VM2 IM1 cosine omega 2 plus omega 1t plus theta V2 plus theta I1. And finally, we are on the part where we multiply VB times IB. So this is going to look like 1/2 VM2 IM2 cosine theta V2 minus theta I2 plus 1/2 VM2 IM2 cosine twice omega 2t plus theta V2 plus theta I2. Okay. So we have these 8 terms, but I want us to notice something. Okay. So one thing that I can note, I'm trying to figure out where to write this down. I'll just do it down here. So this is another simple trig identity. Cosine of negative angle is equal to the cosine of the positive angle. So where this comes into play is that if we consider omega 1 minus omega 2 multiplied by time to be an angle, then omega 2 minus omega 1 times time is the negative of that angle. So effectively, this term right here that I'm underlining in red, and this term right here that I'm also underlining in red, can be combined together because they are sinusoids oscillating at the same frequency using this trig identity. Additionally, we have a DC term right here and a DC term right here that could be combined together. And then we have this guy right here is cosine omega 1 plus omega 2 times t. Sorry. And this guy right here also has an angular frequency of omega 1 plus omega 2. So they could be combined together. And then finally, we have this guy right here, which is at a frequency of twice omega 1. And this guy right here, which is at a frequency of twice omega 2. So effectively, if we multiply two waveforms having two frequencies, we find that our power absorbed oscillates at 5 different frequencies. It'll always actually be 2n plus 1. Okay. So the instantaneous power in a multi-frequency circuit is a bit of a pain in the butt to calculate. Okay, we have a lot of things to pay attention to. So the most I will ever ask you to do on your homeworks or your exam would be a 2-frequency circuit, which I've illustrated how to do here. Now, the average power absorbed by this circuit is simply the DC contributions, right? So that's going to be 1/2 VM1 IM1 cosine theta V1 minus theta I1 plus 1/2 VM2 IM2 cosine theta V2 minus theta I2. All of the oscillating terms, everything where omega isn't equal to 0 effectively, will not contribute to the average power because exactly half of the time they are above the DC level and exactly half of the time they are below the DC level. Okay. Now, what's interesting about this average power relationship is you can get these quantities, or you could get this result effectively by applying superposition to your network incorrectly. And the reason why I say it's incorrectly is because superposition is not supposed to work for power-related quantities, because the superposition principle requires the use of linear calculations, and power is an inherently nonlinear calculation because it depends on the voltage squared or the current squared. In the case of pure sinusoids like this, it winds up working out, but if we had some other type of periodic wave, it likely would not. All right, so the next topic that I want to talk about today is that of effective values. So I'm going to start this off with a question. I hope one of you two guys who are on Zoom will at least attempt to answer it, but if not, it'll be okay. And the question is the average power absorbed by a network equal to the average voltage drop across the network multiplied by the average current flowing through the network?
Yeah, maybe.
So the answer is actually no.
I don't know.
Let me explain why. Okay. So if we have a system where the voltage drop across our element or network of interest is sinusoidal, Vm cosine omega t plus some phase angle theta v, and our current I of t, current flowing through our network of interest, is of the form Im cosine omega t plus theta I, we know that average power for such a system should be 1/2 Vm Im cosine theta v minus theta I. We proved this a couple of class meetings ago. What's the average value of that voltage? So if I plotted my voltage waveform, here's V of t, here's t, with an arbitrary phase angle, for a pure sinusoid, exactly half of the time the signal is above the horizontal axis, and exactly half of the time the signal is below the horizontal axis, which means the average value of the voltage is actually 0 volts. We would see the exact same thing for a current if it's a sinusoid, right? So if the average value of the voltage is 0 for a sinusoidal system, and the average value of the current is 0 for a sinusoidal system, 0 times 0 cannot equal 1/2 Vm Im cosine theta v minus theta I. So what seems like should be intuitively correct turns out to not be correct in a system like this. The concept of effective values is a way that engineers have developed to kind of make the intuition work, okay? So an effective value for a periodic signal is an equivalent DC voltage or current which delivers the same amount of average power as the periodic waveform to an arbitrary load. So effectively, for a DC system, our average power, P average, can be written as the DC voltage squared divided by some resistance that we're trying to deliver power to, or it can be written in terms of a DC current as well. Well, this would be I DC squared times R. For an AC system, average power can be written as 1 over capital T, where T represents the period of our waveform, times the integral from lowercase t to lowercase t plus t. Effectively, I am just integrating over exactly one period times, or excuse me, the integral of our periodic voltage waveform squared divided by our resistor value, or in terms of current, and I guess technically these should be primes because I have a t in my limits of integration. So what the effective value is we simply set these two equations equal to each other and solve for the DC quantity, because that gives us a DC value that delivers the exact same amount of power, average power specifically, as our periodic waveform V of t or I of t. So we'll actually get the exact same expression, whichever one we choose. So let's work in terms of voltage, okay? So if I equate my two average power relationships, what I'll get is VDC squared over R is equal to 1 over T times the integral over 1 period of my periodic voltage squared, like so. Well, there's a common factor of 1 over R on both sides, which means the actual value of the load we're delivering power to doesn't even matter, right? Those 1 over R terms cancel each other out. And from here, solving for VDC is rather trivial. We just take the square root of both sides. And so we'll find the DC value, which I'm now going to call V effective, is equal to the square root of 1 over T times the integral over exactly 1 period of, sorry, don't need the over R. So it is the square root of 1 over T multiplied by the integral of the period, or the integral over exactly 1 period of the square of the periodic voltage waveform. Effective values have units of, in this case, it will be volts, what are called RMS, where RMS stands for root mean squared. And why we are having units of RMS is because we are taking the square root of the arithmetic mean or average value of the square of the voltage waveform. Through an extraordinarily similar derivation, we could also find that the effective value for a current is the square root of 1 over T times the integral over 1 period of I of T squared. And we'll have a unit of amps RMS. So let's take a moment or two here and put these equations into use to calculate the effective value of some common waveforms. So let's say that I have a voltage waveform V of T. My voltage has a value of V naught for some duration of time, and then it drops down to negative V naught, and it stays minus V naught for the same amount of time that it was positive, and then it just swaps back and forth like so, so that we could call this specific point in time, so if this is 0, and this point in time is capital T, this point in time is capital T over 2, right? So we're saying effectively this length of time defines 1 period. Exactly half of the time the voltage is positive at V naught, and exactly half of the time the voltage is negative at negative V naught. As a piecewise function, our voltage could be described as V naught for 0 less than t less than capital T over 2. And it could be described as negative V naught for capital T over 2 is less than t is less than capital T. This is how our voltage is defined over exactly one period. The effective value of our voltage would be given by the square root of the integral, actually 1 over the period. So this is going to be 1 over capital T times the integral over one period. And since we have a piecewise function, I'm going to break up my integration. So I'll have one integral here from 0 to capital T over 2 of my voltage value V naught squared dt. And then I'll have a second integral for the second part of my piecewise function, where I'm integrating from capital T over 2 to capital T of negative V naught, my voltage value, squared dt. So I'll have my 1 over t. V naught squared is actually just a constant. So I'm going to have V naught squared times the integral from 0 to 2, or excuse me, to t over 2 of dt plus, and now I have negative V naught squared, which is the same as positive V naught squared, which is a constant, so I can pull that outside. Integral from t over 2 to t dt. Sorry, I forgot to close my bracket over there. And what I can do now is I can pull that factor of V naught squared out, so that I'll have V naught squared over t. And now I'm going to do the integration. Well, the integral of dt is just t. So I'm going to have t over 2 minus 0 from that first term. And for my second integration, I'm going to have t minus t over 2. This is going to leave me with V naught squared over t multiplied by t over 2 plus t minus t over 2. We can see very easily that this term and this term cancels each other out. And this t effectively in the numerator is going to cancel out this t in the denominator, leaving me with an effective value of V naught. So for this square wave, the effective value is simply the magnitude of the square wave. Now, if we had a series of rectangular pulses instead of a square wave, so I'm just going to draw this on top, but we're not going to do the analysis because I asked you to do it in your homework. But if we had a signal like this, that I'm doing here in blue, so where we effectively didn't have the matching negative rectangular pulse, we'll find out that our effective value will be appreciably different, okay? So just because it happened to work out to be V naught for the square wave that we're dealing with here, if we change the shape of the square wave by either cutting off the negative half cycles or changing the duty cycle, and what I mean by that is changing the duration of how long it stays positive to how long it stays negative, we'll get different answers. Okay. Another very commonly used waveform, in fact, the one that we've been using for the last several class meetings, is a sinusoid. I'm going to draw a picture of a sinusoid again. I know that you guys know what they look like, but it'll help us recall a few important things here. And just for the sake of argument, I'm going to say that this is a current waveform. And here's our signal. I'm going to take our period to be the distance between successive positive peaks. So I'm going to call this time lowercase t, and the time that corresponds to the next peak to be lowercase t plus positive t. Okay. So our current as a mathematical function could be written as Im cosine of omega t plus some arbitrary phase angle, theta I. And for me to apply my effective value equation, I have I effective is equal to the square root of 1 over t integral from lowercase t to lowercase t plus capital T of I squared dt prime by definition. Now, we are going to need to figure out how our period capital T relates to our angular frequency omega in this case. So recall, some of you guys learned this as early as engineering 121 actually, that the period T is the inverse of the linear frequency f, and our linear frequency f is simply our angular frequency omega divided by 2 pi. So from this, we can find that our period T is 2 pi over omega. So we're going to put that result into our expression. So 1 over t is going to look like omega over 2 pi. we're going to integrate from lowercase t to lowercase t plus 2 pi over omega. And our current waveform squared is going to be 1/2 Im squared plus 1/2 Im squared cosine twice omega t plus twice theta I. And all these t's should be primed since t shows up in the limits of my integration. Okay. I got that result for I squared by using the trig identity that I identified earlier today. And also when we dealt with instantaneous and average power for the first time. All right, so what I'm going to do now is I'm going to break this integral up into 2 parts. Close that. All right, and here we go. So let's focus on this integral right here first. Okay. So I have the integral from, or effectively the integral over exactly 1 period of a sinusoidal signal that's oscillating twice in that 1 period duration. So what I mean by that is if I tried to draw this, and I'm going to superimpose it on top of our current waveform, so this is going to be part of I squared, it would look something like this. It's oscillating twice in the amount of time it takes for the current to oscillate once. But if we integrate over that duration of t, well, exactly half of the time our current is, so let's split this up, above the horizontal axis, and exactly half of the time the current is below the horizontal axis. So we're just integrating this sinusoid effectively over 2 periods. This squared twice frequency term here. So this integral actually just goes to 0, because if we integrate a sinusoid over any integer number of periods, the result has to be 0, which leaves behind only the DC contribution to the square of the current. Okay. Well, all that stuff, the 1/2 is a constant term, the Im squared is a constant term, so we can take it outside of the integration. And so in doing so, what we're going to have is the square root of omega over 2 pi times a factor of 1/2 Im squared times the integral from t to t plus 2 pi over omega of dt prime. So if we do that integration, we'll have t plus 2 pi over omega minus t. Obviously, this bit cancels this bit, and we have a factor of 2 pi over omega multiplied by omega over 2 pi, so those guys cancel each other out, giving us 1. And what we find here is that the effective value for our sinusoidal current is just the magnitude of the sinusoidal current divided by the square root of 2. I'm going to put a box around, actually, effective. I'm going to put a box around this because it is a very important revelation. Okay. So, why this is so important is because the effective value of a sinusoidal waveform is simply the magnitude of the sinusoidal waveform divided by the square root of 2. That is independent of the angular frequency. It is also independent of the phase angle, which means here in the United States, where our sinusoidal signals that are generated by our electric utilities, they oscillate at a frequency of omega is equal to 120 pi radians per second with a phase angle, whatever we start measuring at. In most parts of Europe, their voltage distribution oscillates at a frequency of 100 pi radians per second. So two different frequencies. However, the analysis required to determine the effective value and use the effective value quantities is exactly the same. It's simply the magnitude of the sinusoid over the square root of 2. All right, so the last thing that I want to talk about here today is we're going to use this effective value relationship as a jumping off point for tomorrow's lecture. Okay. So for a sinusoidal system, we know that the average power, P average, is given by 1/2 Vm Im cosine theta V minus theta I. We could rewrite this expression as Vm over the square root of 2 times Im over the square root of 2 times cosine theta V minus theta I, or simply V effective times I effective cosine theta V minus theta I. Okay. So effectively, the average power is now in some way related to the effective values for voltage and current, which are in turn related to the average values of the square of our periodic waveforms. Okay. this expression, P average here, is the real part of the following mathematical operation. V effective angle theta V times I effective angle theta I conjugate, where we can call V effective angle theta V an RMS phasor voltage V, and we can call I effective angle theta I conjugate the conjugate of an RMS current I. And this quantity here, V RMS phasor voltage V times RMS phasor current I conjugate, is what we call complex power S. We're going to get into this in much more detail on Wednesday, but the complex power is simply a mathematical construct that electrical engineers have developed to be able to use or to develop power relationships that tell us a lot about how a load behaves in a steady state sinusoidal system using only effective values, so that we don't have to carry on a bunch of extra information that isn't really pertinent to what's going on. Okay. So this is where I'm going to stop for today. We are going to spend our next class meeting talking about complex power and all of its constituent parts: apparent power, average power, reactive power, and power factor. And then if we have time, we will also talk about power factor correction. Friday's lecture will be spent working problems related to complex power and its constituent parts, as I'm going to wind up giving you guys something close to a dozen equations on Wednesday's lecture. All right, so unless anybody has any questions, that is enough out of me for today. Have a great rest of your day, and I will see you on Wednesday.